here we have it's now person talking. Yeah, very good. Thank you.
Well, thank you for the lovely introductory talk. So I'm going to be presenting as quickly as I can a update on some of the research that we've been doing at the U.S. Military Academy. This is work that I've done with Bastion. The title of the talk is Relevance Scoring as a Feature of Metacognitive Artificial Intelligence. Briefly, I'm going to give some outlines in terms of the practical and philosophical challenges that motivate metacognitive AI, but I'm going to hone in on the key challenge of incorrigibility, or the lack of corrigibility that a lot of these artificial intelligence models have, and how the certainty, competence, and ultimately relevance framework that we've developed at USMA can be used to address this problem of corrigibility and how that relates to the metacognitive task. And then finally, I'll give some presentation on the actual empirics that we have found so far with respect to these relevance structures, and then give an indication of the next steps and how we can use this to actually build metacognitive AI systems. And so, briefly, I think it's already been somewhat mentioned, the general practical challenges that we have with most of these AI systems are that there are distribution shifts that actually limit the applicability of these models outside of their training. Conventionally, it lacks adaptability, explainability, and trustworthiness. Like, the models will insist that they've done something even though they've demonstrably not done that, or that the inputs that they have are correspondingly producing correct outputs. But strangely enough, training these further actually leads to less belief revision, so they actually become less corrigible as they get further trained. They're more likely to actually do corrections early on, but then afterwards they lock in thinking that the data that they've been trained on, that is actually a picture of the world. And that's a big problem. And underlying that, actually, in addition to having frequent issues, pulling it back slightly to a philosophical bit. So, unfortunately, there's a dead economist, Frank Knight, who kind of came up with this relatively unformalized concept of Knightian uncertainty. If you're familiar with Donald Rumsfeld's Unknown Unknowns, same kind of concept. This is different from risk in that it's present in situations where there are actual things that are outside the scope of modeling or outside of the scope of things that can be relatively centrally quantified or even conceptually quantified. They typically manifest in four forms: after ignorance, what you don't know; practical indeterminism, what you can't really model; agentic novelty, when you have multi-agent systems interacting with each other and they actually create new strategy spaces; and then just problems with predicting competitive recursion. So again, these are economics terms, but they actually have practical challenges that you face when you are building AI systems. And there really isn't a good solution here, but one way is you have problems of self-adaptation. Models are actually vulnerable to Knightian uncertainty because they are unaware that they are in a position where they actually have to update. And metacognitive AI is developing a programmatic solution for precisely these sorts of challenges. We want self-aware, self-monitoring, self-correcting AI that can recognize what I know is not actually applicable. And how do we get that? Well, part of that actually requires the ability to be corrigible and actually understand that these systems are fallible and might need to be updated. And so figuring out quantitative, probabilistic ways to get these machines to do that, that's a challenge. And this is where the certainty and confidence framework is coming in. So certainty is really just any intrinsic measure of the probabilistic assignment that these models have. The work that we have, at least on classification tasks, you have a matrix of pairwise differences between all the possible assignments. And traditionally, we go with the maximum posteriori, we select the most likely assignment, and that's the correct answer. But what if you're in the case where between 100 labels, the first label you have a pseudo-probability value after you do softmax adjustments, logits of 0.51, and then the next most likely label is 0.49. It's not really a compelling argument that given those input features, it's going to be label 1 versus label 2. That's barely a fair coin toss favoring label 1 versus label 2. So this isn't actually something that indicates intuitively a high degree of certainty. But certainty scores can really be generalized to anything else. We're just using this as an example of the classification task. We similarly have a notion of informativeness, which is a relative threshold capturing how much of a model is actually determined. If you had an informativeness of 1, this means that you're basically looking at a pure coloring of a label or like a pure indicator function. In general, most of the systems that we have aren't going to actually theoretically allow for an informativeness of 1. Most of the time, we actually have like a stochastic process or a mixed model process that we're looking at. But in the case of trying to train like an AI system on what would an input code, look like, that is actually something that conceivably could have an informative one. That string of digits is only ever going to be interpreted one way and executed one way. And that finally leads into the final component of competence. Competence breaking down into components of competence in terms of the relative tasks that it's good at, and then the empirical performance of a model given its score. And finally, the competence hierarchy where E above, if E is below this alpha threshold of 0, we just say these models are incompetent. I'll define what we actually mean by empirical competence on the next slide, but it's important to actually have a hierarchy where at the very bottom, you're competent. Then you're relatively alpha amateur. So you're amateurish, you don't actually capture that informativeness threshold, but you're better than being incompetent. You actually possess some ability to convey information on input features. If you're above this alpha threshold, you would be relatively competent. You're performing better than what a purely random or mixed model would say. And then if your component competence is actually, or if your empirical competence is better than this component competence, we would say this is an expert level system. And then finally, if you have something above complete component competence, we would say that this is a prescient system. In the papers where we introduced the certainty competence framework, this would actually mean that this is a system that has one-for-one every input it correctly guesses the output. That would be something that would happen if you're actually modeling like y equals x, or y equals 2x plus 1, something where there is in fact an underlying purely deterministic function, and not something that actually has a stochastic component. And the fundamental theorem of the competence hierarchy is that the true positives of a competence system are separated by at least that alpha parameter from the false positives predicted by that. So if something actually has a low certainty score, it is much more likely to be distributed as a false positive or something that was incorrectly classified as something belonging to that label than something that would be a true positive. So this is both a formal mathematical proof, but something that we've empirically found across multiple models, across multiple modalities. True positives from competent models are separated from the false positive according to their certainty scores. And this is something that we've seen time and time again with respect to classification tasks, but we are actually asking ourselves, can this generalize to generative systems? And we believe we can do that by introducing the notion of a relevance structure. So here's a formal mathematical definition of what we mean by a relevance structure. A relevance structure is given by a signature where you have a universe, a partially ordered universe with a ground atom, 0, which is the least element. You have an intersection operation, what I'm calling a pre-complement operator, and then finally an order operation. And we just require that this partial order, the ground element 0, such that every other element is at least as great or greater than 0. An intersection operation which behaves as we expect intersections to behave in a post set. So for any 3 elements in this partial ordered set, the intersection between x and y would be less than x and less than y. And if z is less than x and is less than y, then z is also contained below the intersection. So it's a maximal in that respect, or it is in some respects the greatest lower bound. And then we also require that our intersections are symmetric, transitive idempotent. And then finally, for this pseudo-complementary operator, or the pre-complementary operator, we just mean that the relative complement of y with respect to x intersect with the relative complement of y with x with respect to y would be something equivalent to the ground element, and this is also similarly maximal with respect to this property. And then finally, we want some order preserving map that maps our partially ordered set into the non-negative real numbers such that it respects the partial ordering, and that the only thing that is uniquely 0 would be 0.
2 minutes.
Oh, 2 minutes? Oh, okay. So I'll be as quickly as possible. So what can be given in relevance structure? Well, practically anything of interest, because we see this with respect to any discriminative tasks, but because it extends from multi-post sets, or multi-sets into post sets, it extends into general topologies, lattices, can be applicable to formal concept analysis, gating algebras, and then relevance structures themselves as partially ordered sets are capable of being given relevance structures. There are 3 scores that are important. There's exploratory, parsimony, and balanced. These are actually something that allow us to define a general notion of empirical competence, where we have a certainty score or competence score as the weight, providing the weighted sum of our relevance scores. And relevance structures of Cantor spaces, Baire spaces, those can be given relevance structures. Any relatively pseudo-complemented lattice can also be endowed with the pre-complement function and a value map, which gives it a relevance structures of any gating algebra as mentioned. And then just practically speaking, image identification tasks with bounding boxes can be used to generate the underlying topology, which gives them a relevance structure. I can skip some of the category theory examples here, but the key takeaway is, although metacognition may not solve this, it can at least address factor ignorance and agentic novelty, and relevance can be used to allow AI-enabled systems to recognize boundaries of their own competence, identify out-of-distribution data. This allows us to address incorrigibility by heavily penalizing overconfident incompetence as demonstrated in training, and in the field, in production, when encountering novel information, if something falls outside of the scope of its boundaries according to the competence hierarchy, this would be giving us some indication that this is actually novelty and would introduce a human loop. And then finally, again, we pull back to what are the imperatives of this? Well, it outperforms state-of-the-art energy-based data protection methods on different data modalities, as seen in this table. So looking at the resonant models just alone, across the board, the Omicron-related statistics perform better than the energy-based data protection tests and reckoning. So far, we've seen this framework applied to discriminative tests, classical architecture, discriminative tests to craft data, discriminative tests to logic tensor networks, and we're currently using it for visual question answering tests, natural language inference, and concept production. Are there any questions? Sorry, trying to rush under the 15.
Sorry, but that had to do.
I totally understand. I just had to skip some of the categories.
Really impolite.
Yeah.
Questions, please.
It's a lot of formal stuff, sorry. Any questions? Okay.
So, I had a question.
Quick question.
Fundamental theorem of competence. Is this your result or?
Yes, this is our result. So, given the definition that we have of certainty and competence, there are hard distribution-independent results that actually indicate that once you cross this alpha threshold into competence, you have a hard guarantee that you will have a separation between the true positives and the false positives. Or otherwise, you will have, if you go below that, you will have micronumerosity with respect to samples that you have. So you might have 20 samples, and one of them might be a false positive. So you have other problems. But once you have a sufficiently large number of samples, you're guaranteed to actually have this alpha threshold. And that n varies by what your alpha threshold is. So the more informative you want your model to be, like you'll certainly have more of those samples, but generally speaking, anytime you have an informativeness above 0.003, you're guaranteed to have this separation of the means between true positives and the false positives when you have competence both globally and also within categories. So you might have a model that is actually globally incompetent, but might be competent in 2 or 3 categories. That result applies for those individual categories. So you might not have that guarantee globally on any input, but you could use this as a relative domain expert and then ensemble models together based on their relative competence. And so you can make competence weighting circles that way.
If you're interested in theories and empirics of this, we have a paper in ATM transactions on probabilistic machine learning.
I think it's open access. And that has a proof of the competence hierarchy.
Thank you.